Hi friends, in this session we will discuss reading number 1 of Market Risk FRM Part 2. This reading is Estimating Market Risk Measures, Introduction and Overview. Now this reading resembles your FRM Part 1's Value at Risk discussion. Value at Risk as in from book 4, first two topics. Okay, so first two topics were on value at risk and some detailed discussion on value at risk. Now we will repeat same topics here, approximately like 70%, just a second. Approximately 70% topics are exactly same, so there is no difference, and we will have 30% new discussion, 30% new topics. Okay, so we will have to discuss those topics and I will focus on those topics. Now in this reading or from this reading, you will get approximately 3 to 4 questions in exam based on the past examinations. This reading plus your reading number 2, which is on non-parametric approaches, for value at risk. Okay, so both the readings, reading number 1, reading number 2, both are on the value at risk only, and these readings covers the repeated discussion of FRM part 1, but there is some difference, or there is slight difference in FRM part 2 compared to FRM part 1. And as I told you, like from this reading you will get approximately 3 to 4 questions. If you combine both the readings, reading number 1, reading number 2, you will get approximately 4 questions. Okay, so 4 questions for sure. So if you get 4 questions from reading number 1, generally then you don't get extra question from reading number 2. Reading number 2 is a very small discussion, and if you get say 3 questions in reading number 1, then you may get 4 questions combining reading 1 plus reading 2. Very simple. And if I tell you like what are these questions, then you will feel okay, so these are the easiest questions. I will give the example of questions. Calculate VAR. Z is provided to you, Z is provided to you, sigma is provided to you, everything. Okay, so ready-made question. Second question is historical simulation VAR. Okay, historical simulation. So all the lowest 10 losses are provided to you, and you are expected to calculate 95% VAR, that is the 5% significance level. Again, very easy. Then expected shortfall, and using the same method, the lowest 10 values are provided to you, and again you have to calculate expected shortfall using the 95% confidence level, obviously 5% significance level, and so on. Now all this discussion is repeated discussion. We know this discussion from FRM part 1, and as I told you, like I will assume you already know this or you remember this discussion. But in FRM part 2, when you get questions on these topics, okay, this is the area where students make, like most of the students make mistake. Why? There is a reason. The method we used for the calculation of value at risk in historical simulation and for the expected shortfall in FRM part 1, this method is 99% same, but there is 1% difference. Okay, I will tell you what is the difference. And this difference creates problem in exam, and you need to, or you must remember the difference. What is the difference in calculation of value at risk in FRM part 2 versus FRM part 1? For same method, there is difference in calculation. Now let's see. I will assume some lowest values or returns. Okay, so let's take losses and lowest 10, where n is equal to 100. So out of 100, we are just taking lowest 10. I am just assuming all the values. All the values are in millions. Okay, so all the values are in millions. So let's say we start with the 17 million, 15 million, 14.5, 13, 12.2. I'm just taking random values here. Okay, and 10.2, say 10.1, 9.8, then 9.5, and then 9.4. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So more than enough. Okay, so these are the 10 lowest values. Now in FRM part 1, if GARP asks you say question on calculate 95% VAR using historical simulation, of course, because we have the data for historical simulation. Now our approach from FRM part 1 is we take the fifth lowest value. So this is first, second, third, fourth. This is fifth lowest value. Fifth lowest is your VAR, value at risk, and average of these values. You have to exclude the fifth value and you will take 4 values, and this becomes your expected shortfall, obviously in the historical simulation setup when you are provided with the loss data, right? So this was our approach in FRM part 1. Now in FRM part 2, the approach will change. If you are my student from FRM part 1, in FRM part 1 itself I told you, like, there is confusion, not confusion, there is debate or dispute among the risk managers, like what should be the exactly value at risk, the VAR value. Okay, so should we take, this is what risk managers, those who are setting up all the, or designing, or authors, those who are writing books for risk management, so their confusion is, or their argument is, should we take this fifth value as value at risk, or we take this value as value at risk, or should we take average of these values? And that's the confusion. Okay, so in FRM part 1, the author who worked on a content of this particular value at risk section, he took this particular value as value at risk. But in FRM part 2, the author assumes this particular value as value at risk. Okay, I hope you got the idea. So what you have to do, you have to take the 5%. Okay, so 5 values, hundreds, 5% is 5 values, and next value after that is your value at risk. So this is for FRM part 2, this is for FRMP1. And obviously if you change the value at risk, then automatically your expected shortfall will change. Now your expected shortfall in FRM part 2 is average of these values. Okay, so using 5 values you will calculate expected shortfall. If we assume, say, there are 500 values, okay, and again you are supposed to calculate, say, 1% VAR, you have to apply the same logic. But now how to find out, or do we have any rule which gives us the specific information about which value to select in FRM part 2? So in FRM part 2, the rule in historical simulation, remember we are discussing historical simulation here. So in historical simulation, the rule is value at risk is equal to the value alpha multiplied by n plus 1. Okay, so alpha multiplied by n plus 1th value is your value at risk. Now we will put it in our perspective, use this formula in our case. So we are calculating value at risk for 95%. So value at risk for 95% confidence level. Obviously our significance level becomes 5. So 5% multiplied by 100 plus 1. So this is 5 plus 1 is equal to 6th value. And if you come here, you will see first value, second value, third value, fourth value, fifth value, and this is our 6th value. So this is our VAR. Okay, so this is what you need to remember. In exam, when students get expected shortfall question or the value at risk question, they generally get excited. Okay, and in that excitement they make this mistake because you carry your baggage or your information of FRM part 1 in FRM part 2, and this leads to confusion. Even if I tell you specifically, in exam there are chances like you will face the same confusion again. So remember, in FRM part 2 we are using this particular formula, that is alpha multiplied by n plus 1. You have to remember this formula so that you don't make any mistake. Okay, and GARP was asking these questions again and again, like the expected shortfall. Students used to get in like 2019, till 2019 we collected, like we discussed questions with students. So till 2019 students used to get two expected shortfall questions. two expected shortfall questions, more or less similar, and you are supposed to calculate the expected shortfall. And what was the reason for this? Because GARP knew students make mistake in this area, and that's why GARP was repeating those questions again and again in the examination. Students used to get historical simulation question in FRM part 2. And why? Right? So the reason is this: because GARP knows students make this particular mistake, and GARP will provide you option. GARP will provide you this particular option. Okay? So you will get this option and this option. You will get both the options. And that's the reason your confusion will increase in exam. So you have to make sure you don't fall for all these tricks. Okay, make sure you are confident and you know your approach in a very proper manner. So you must remember all these things. Now next. So this approach, as we all know, this is non-parametric approach. This is non-parametric approach, right? This is a historical simulation approach. Now we will see the parametric approach, and again here also we have one more extra discussion. Parametric approach. In parametric approach, we will see two types of VAR. First is normal VAR, and second is log normal VAR. This is again purely repeated discussion, same as FRM part 1. Okay, so same as part 1. Okay, so nothing new here. So the formula, I hope you remember formula, and if you don't remember formula, please revise your FRM part 1's curriculum, because we will need CAPM discussion, CAPM in obviously book number 5, not in book number 1. Then we will need Black-Scholes and Merton model when we discuss the volatility smiles, and we will need complete valuators discussion for this. We will need fixed income discussion to discuss market risk term structure. Okay, so there are a lot of repeated discussions or common discussions or extended discussions which are coming from FRM part 1. So make sure you know or remember all the FRM part 1 concepts. So with weak FRM part 1 concepts, it is very difficult to prepare FRM part 2 properly. Okay, now value at risk for the given confidence level. So our formula is minus mu. This is return. Just writing down the formula, you know how to do the calculation, and then Z. Okay, Z for that specific percentage. And our values were, so for 95% we use the value 1.65. This is Z tail left, Z value 5% left tail. Okay, and for say 99%, this value is 2.33. Okay, so these are the values. You already know all these values, right? So again, nothing new here. Now, log normal VAR, ln VAR. Okay, this is not very correct way to write this ln VAR. I will just write it as full only. Okay, properly. Log normal value at risk. Okay, now just very basic thing, we will need this calculator. So make sure you have calculator, and wherever the calculation is required, we will do the calculation. Now here in log normal VAR, our formula is same as, like, the base of the formula is same, but we use formula in slightly different manner. So this is your portfolio value multiplied by 1 minus e to the power mu minus sigma into z. So this particular part, sigma into z, this is exactly same as your discussion, like this normal VAR, same discussion, right? Except for the symbol changes. Okay, so symbol here is, this is plus mu minus sigma into z. So the net result of this particular part, only this, the power part, will be negative. Okay, and if you are calculating daily VAR, based on your calculation requires you to calculate daily VAR, then return part will be approximately 0. So we don't consider that. So we directly go with the minus sigma into z, like this, very simple. Now you have to use these values. Simply put it in the exponential, minus 1 multiplied by your portfolio value. Let's assume our portfolio value is 100. 100 multiplied by 1 minus e to the power, let's assume the return of 0.02% return, standard deviation of 10% multiplied by 1.65. Okay, so these are our values. And now we'll use our calculator for this. Just increase the size. I hope this calculator is visible, like whatever calculations we are doing. So now here 0.02 minus bracket open 0.10 multiplied by 1.65 bracket close, answer is in negative second exponential minus 1, remove this minus sign, multiply by 100, and your value at risk is 13.50 approximately. So 13.50. okay, so value at risk at 95% using these values. Now this is very, again, simple discussion. So if you understand normal VAR, it is just we are using the exponential term to calculate the log normal VAR. Now when to use log normal VAR and when to use the normal VAR? If you calculate normal returns, if your return calculation methodology is normal return, so just see here, if your return calculation methodology is normal return, then we will use normal VAR. If you are calculating log normal returns, then we will use log normal VAR. Very simple. So assume the yesterday's price or the old price is PT minus 1 and new price is PT. Okay, PT minus 1 is the old price. Just old price, and this is your new price. So obviously for normal returns we do this calculation. So this is PT minus 1 divided by PT minus 1, and this gives us the return, right? So daily, it can be daily return, monthly return, and so on. So this is normal return. So if you calculate return using this particular method, then you have to use normal VAR. This you need to remember for exam as well. In exam you might get this theory question. So you have to use this particular formula. On the other hand, if you use or calculate log normal returns, in this case, if your returns are log normal or continuously compounded, then you have to use obviously log normal VAR, right? And what is the method of calculation of log normal returns? It is very simple, PT divided by PT minus 1, and then simply press ln. I will give the example in case you don't know, and obviously in case you are not my student from part 1. Okay, then you will have this confusion. So 120 divided by 100 and simply press ln, and you will get this return 18%, 18.2, which means this is like continuously compounded return. Okay, so very simple, very basic, right? Nothing special here. So I hope you understood the basic concept here. The basic concept is, for normal returns use normal VAR, for log normal returns use log normal VAR. In real life, irrespective of which method you choose, the log normal VAR or normal VAR, value should be same, or it should not affect your real life calculation, because at the end this is the adjustment approach. Because you are using the log normal return, we are using log normal VAR. If you use normal return, we are using normal VAR. The value of both of these value at risk should be exactly same, or should be like same only. Okay, so that's what you need to remember. And in exam, if you get question, again you have to remember this, like the value should be same. Now statements to remember. Okay, again the repeated statements. These statements are same as FRM part 1. You already know these statements, but again I will write exactly what's given in GARP's curriculum. So you have to remember, if geometric return follow normal distribution, then natural log of asset price follow normal distribution. And if the price, you assume the prices are like normal, then price follow okay, this is the first statement, and both these statements are more or less same. It means the same thing at the end. Okay, so the statement goes like the geometric return, that is a ln return. Geometric, this is geometric return. Okay, so ln return, if the ln return follow normal distribution, so if you take the ln of like your returns, okay, so you use ln, that is continuously compounded returns in short, but I'm intentionally not using continuously compounded here because it might create some confusion for you. So your ln returns, that is geometric returns, remember like this, you should know the statement like this: if the geometric returns follow normal distribution, that is you calculate continuously compounded return, it follows normal distribution, then the natural log of asset prices follow normal distribution. Natural log of asset prices follow normal distribution. If you calculate ln of asset price, natural log of asset prices, and then you plot it on the distribution, it will follow normal distribution. And prices will follow, prices without any treatment will follow log normal distribution. Okay, so this is very simple. And here always remember just a very short trick: in one statement there is only one ln. Okay, so like if the geometric return follows normal distribution, I'm repeating this again and again so that it fits in your mind. Okay, so if the geometric returns follow normal distribution, remember, if the geometric returns follow normal distribution, this means first, this means that the natural log of asset prices, if you take ln of asset prices, this will follow normal distribution. ln of p will follow normal distribution, and p will follow log normal distribution. I hope you understand. This is log normal distribution bound by 0, okay, and skewed to positive. So this is the statement. Again, this is again the further explanation for the statement, which you need to remember. Very easy, not very difficult thing, right? Now next discussion is estimating coherent risk measures. Okay, now this coherent risk measure is the same discussion again, but here we don't have all those properties like monotonicity, subadditivity, positive homogeneity, and translation invariance. So all those discussions are not covered here in this particular chapter. We have this in next chapter. Now we don't have to bother about this, but here this coherent risk particular part, this learning objective mainly talks about the spectral risk measure. The spectral risk measure, again we discussed this in FRM part 1. What is spectral risk measure? So in spectral risk measure, we divide, or we create a spectrum of this distribution. We divide it into like multiple parts and equal parts, and based on this we provide weights. So if this is your normal distribution, we create a spectrum here, and we use this particular spectrum to calculate value at risk. If you are calculating the expected shortfall, okay, and this is say 5% spectrum, then the average value of this 5% spectrum is the expected shortfall, right? Simple. So expected shortfall is also spectral risk measure or the coherent risk measure. Okay, so you have to remember like this. And here we are providing all the weight in this section. Okay, so specifically to this tail, and this weight is simply your significance level divided by total number of values in tail, like that. Okay, so this much weight is provided. Or simply we can take like this, say if you have, just a second, if you have say 5 values in the end, so we are providing 1/5 weight to each value. We can say we are taking average of 5 and providing 1/5 weight to each value. These 5 values is one and the same thing. This is just like mathematics, like how you say the mathematics, it depends, right? So, but the calculation is same. So this is spectral risk measure. In spectral risk measure, if you take this particular value, which is that value at risk value, under the spectral risk measure, we provide 100% weight if this is war. Just for now, assume this is war. Okay, so this is your war. So we provide 100% weight to this particular value to calculate value at risk. Okay, so in spectral risk measure, to calculate expected shortfall, we take this last spectrum or the 5% spectrum and provide like equal weights and calculate expected shortfall. This is again the weighing scheme for expected shortfall. Now if you consider the value at risk, in value at risk, we take that cutoff point and we provide 100% weight to that particular cutoff point. Very simple, right? So this is spectral risk measure. Now I have to generally, like, the statement to remember is like the general spectral or the coherent risk measure divides complete spectrum, as in the distribution, in equal parts and put weight based on risk aversion. Okay, so risk aversion, as in if you are using the general, there is one more specific coherent risk measure, which is a general risk measure. This is again as per author. Okay, general coherent risk measure, coherent risk measure. Now here we will put weights. I told you, like in expected shortfall, we are putting in the weights in certain category. For value at risk, we are providing 100% weight to one particular value which falls on the value at risk boundary. Right, so this is what we are doing here. But in general coherent risk measure, using the risk aversion of the investor or like the trader, so we put weights. Now here, because this is just the information statement, you don't have to worry about the calculation, because in exam, like how will you know what is a like risk aversion level and all? So that's not discussed here. So this is just a theoretical discussion, like this is how you can do it. Okay, I don't know who is doing it, but you can do it. Okay, generally in finance, people prefer a simplistic method. Okay, so as simple as possible, or predefined or defined method. Okay, now here, let's again draw distribution. Okay, and on this distribution, say we want to calculate value at risk. Okay, so our goal is to calculate value at risk. Let's assume this is the particular value, or for better understanding, so this is that point where value at risk lies, right? Now here at this particular point, we already understand, or we already know, like we are not using the population parameters. Like the return we took, say maybe it is for the 12 months, or maybe it is for 24 months, or even for like say 10 years. But we are not taking population value. We are mainly focusing on the sample, right? And samples provides estimates and not the accurate picture of population. This is what we know from the FRM part 1's quant section, right? So we are, even if we don't say it again and again that we are using sample, but we are using sample. Okay, even if you are taking 24 months past data, we are using sample, right? And if you use sample, then the estimation is prone to error, right? So if you decide like this is the value at risk, actual value at risk may lie in between this range. Okay, now next learning objective is about the calculation of this particular range. That is, we have to calculate the confidence interval for value at risk. Why? Because we know we are using sample and we want to know like what is our confidence interval for specific value at risk. Very simple discussion. Now here, whatever we are going to discuss after this particular point, I have very simple note for you. This particular learning objective is not testable. Like I will frame it as a risk manager. There is very low probability that this particular learning objective will get tested in examination, because calculations are very complicated and it is very difficult to calculate or solve this particular question in a given time. It requires more than 5-10 minutes to solve, and a lot of formulas are there. So don't bother about the calculation, just understand what's happening here, what is the methodology. Okay, now first I hope you understood what is our goal, right? So our goal is to simply calculate the confidence interval. For confidence interval, we have this formula. Okay, so I'll explain this formula in detail. Then standard error of Q, just a second, multiplied by Z. Okay, so Q, let me write Q in proper manner. Okay, so Q plus standard error of Q multiplied by Z is greater than value at risk, which we calculated from our sample data, and then this value at risk is greater than, in simple terms, like this is the range of value at risk. Okay, this is a confidence interval. Simply Q minus SEQ multiplied by Z. Fine. Okay, now this particular Q comes from a specific formula. So SEQ formula is under root of P1 minus P divided by N divided by F of Q, function of Q. Okay, I will explain what is F of Q and everything, and we need to directly take the illustration for this. And as I told you, like, you don't have to bother about full calculation, just see it once to understand what's happening here. This is bin width, this is bin width probability mass. This means if you consider this as a confidence interval and this is your bin, then you are calculating the probability mass here. Okay, so this much mass, so this. Okay, this is our goal. We will get this cutoff point. Using this cutoff point, we have to calculate the mass. Then this Q is your bin. I hope you understand histogram, and from histogram what is bin, right? So Q is your bin. This is standard error of bin, that is bin width, and this is your Z value. So your confidence level, confidence interval will depend on what confidence level you choose. And this is your confidence interval. This is your VAR, and this is confidence. Very simple discussion, right? Our discussion will become slowly difficult. Let's see how it goes. Okay, now the illustration. This illustration is from GARP. Okay, so now illustration is, you have to estimate 90% confidence interval for 95% VAR. Okay, so remember, confidence interval is two-sided like setup, right? So if you take 90% confidence level for confidence interval, this means on left 5%, on right 5%. Just to show it on the distribution, very bad shape of distribution, I'll just rewrite. Okay, redraw. Now see here, if you want to calculate or estimate 90% confidence interval, then 5% here and 5% here. And for 95% VAR, we only take left side, left tail, right? So left side. So here 5% VAR will lie here. Okay, so the cutoff point of both of these is like more or less same. But we are estimating, you have to remember this, we are estimating confidence interval 90% at 90% confidence level, but for 95% VAR. Okay, so this thing you need to know very clearly. Now sample size is equal to, let's take 1000, and bin width is equal to h is equal to 0.10. Okay, now here our Z value, because for both the cases we have 1.65 only 5% intel, so 1.65 is our Z value for 5% significance level. Now first step, again, as I already told you, you don't have to bother about this particular calculation. If you can remember, like remember it, or don't bother about it. Say first is range Q. First we will calculate range of Q. So this is your 645, actually 645 plus minus 0.10 divided by 2. Now this particular 0.10 is your bins width, this, okay, and this bins width is quoted in Z terms, okay. This is on the Z scale, so 0.10 is on the Z scale. We are calculating range of Q, that is for the confidence interval building, and that's why from 1.645, if you take like this, and this is 1.645, remember 1.645, so that's why this will land on right side. So we want this particular bin, okay, this particular bin, okay, and for this we have to use this bin width divided by 2, left to Z value and right to Z value. This is what we are doing here, okay, and the result of this, I already have the result. So 1.595 and 1.695, like this. So this particular cutoff, so this cutoff and this cutoff. I'm just say zooming this bin, okay. So this bin will be very small, but I'm zooming this, and you will get bin like this. So 595 and 1.695, okay. Now next is we have to find the mass, probability mass in this particular range, okay, in this particular bin. So for this we don't have to, like, the calculation is very simple. Simply calculate the probability mass here, then probability mass here, and do your calculation. You will get the answer. So the answer is very simple. So 1 minus 0.045, this is coming from this 1.695 and above, minus 0.9446, this is for this, okay. So like this. So simply from 1 you reduce this particular part, and this particular part. We know the total is 1. This part removed, whatever is left is our probability mass for that bin, okay, and the answer is 0.010, like this. If you do the calculation very precisely, then you will get 1.0102, like that, okay. Okay, sorry, 1.04, like this, but again not very important for like calculation part. Now how to calculate the interval? So for interval, this is 1.645 minus 1.645 multiplied by, remember what was the formula? Where is the formula? Yeah, see, Q. So we got our Q, 1.645. Then we are starting with this particular part, minus part. You can also start with plus part. So minus, again, SEQ multiplied by Z. Fortunately, our Q and Z are same, right? So Q is that particular cutoff value, and Z is again our distribution value. Z value, Z score value, and SEQ we need to calculate. So this is your SEQ. So on the SEQ calculation, we have our probability 0.045. This probability is coming from here, and now how this probability is coming? See, we have this particular value 1.695. Now see, if we create bin in this side instead of right side, so 1.695 will come here, and I'm roughly drawing 1.595, and we are interested in tail, right? So we are interested in left tail. So if right side is 0.045, then obviously left side will also be 0.045, and this is probability, right? So this is probability, this is probability. Okay, fine. So very simple. So we are using this particular probability. So P multiplied by 1 minus 0.045 divided by, just a second, divided by 1000, and then this is your bin mass. Bin mass is coming from here. Where is the bin mass? Yeah, this particular bin mass. I'll just highlight the bin mass. This is your bin mass. Then this is your 0.45. Okay. So very simple. We have to simply solve this. And again, you will have the same formula 1.645, but here plus, because we are calculating the range, 1.645, then multiplied by under root 0.045 multiplied by 1 minus 0.045 divided by 1000 divided by 0.010. I hope you understood why I said it is not possible to solve this question in examination. Okay, and the final answer is this. Okay, so I'll just simply show you the final answer. So our value at risk will somewhere, that is your estimation of, sorry, the estimation measure. Okay, so estimation's confidence interval is this 2.6819. Okay, so that's the like your best way to solve this particular question, and that's it. Okay, so don't bother about it. I don't recommend you to like put too much effort on this particular part. Fine. Now last part, and again this particular part is very important. This is QQ plot, GARP's favorite area apart from value at risk. GARP's favorite area. Okay, now understand first the requirement of value at risk. So why do we need value at risk? In value at risk, sorry, so in value at risk, our main purpose is to calculate our risk, the maximum possible loss in the given confidence level and everything. Okay, so you know like what is the statement there. In value at risk calculation, we are using standard deviation, we are using Z value, and this Z value and standard deviation, all this setup requires the assumption of normal distribution, right? Now, the normal distribution assumption is good, no problem with that. But what if your data is not normally distributed? Now, how to confirm or how to check if the data you are taking is normally distributed or not? That's the first requirement. Even before you start your value at risk calculation, you first need to ensure that your data is normally distributed. So to check the normal distribution, we have one particular visual method. This particular visual method is known as QQ plot. Okay, so QQ plot. Fine. So QQ plot's full form is quantile-quantile plot. So what we do here, we create a plot where we put theoretical quantile which means the normal quantile on this axis, and then we put empirical quantile, that is actual data's quantile, in case someone of you don't know quantile is simply you divide complete data in same parts and then you plot your data here. Okay, so we create a quantile scale here on this side and that side. Okay, so on the y-axis you have empirical data quantile, on x-axis we have theoretical quantiles, and then we plot our data. Okay, so this is our QQ line, and just increase the size. If points fall on this particular line, then we assume that this particular data, this empirical data is normally distributed. Okay, just a second. This particular data is normally distributed. Now what's happening here? So what we did, we created a theoretical quantile for normal distribution, the actual normal data. Then we took the actual data, we took the theoretical quantile of actual normal distribution. Okay, so not actual distribution, theoretical normal distribution. We took that data, we create a quantile, and then we map this particular quantile with simultaneously with the empirical data's quantiles. If our quantiles are in, like, both are normally distributed, then we should get our like diagram like this. Otherwise, and don't worry, I will also show you some practical illustration how we execute it in programming. Okay, and I will also show you some samples of QQ plot. Okay, so if we get data like this in exam, this diagram is testable. Okay, so you have to remember, if your data is splitting like this means there is a presence of fat tail. Okay, because on top side this particular data is pulling quantiles on its side, in the bottom side the data is pushing down the quantiles. Okay, so that's why we assume or we consider that there is a fat tail problem. If it is matching approximately, then we assume that the data, empirical data, is normally distributed. If it's not matching like properly, and if say like there is like data like this, then obviously our assumption is the fat tail problem. Now I hope you understood this particular part, like basic, simple. Again, I will just provide the additional like graph. Assume this is your line. If you see data points like this, okay, quantile points like this, then your data is totally, like, not at all normally distributed. If you see majority of the lines are here, but in the tail side it is moving away, then there is a fat tail problem. If it is slightly 1 or 2 points are moving away, then we can say like it is approximately normally distributed, and we will assume that data assuming the normal distribution. Very simple. Now here, before we close our discussion, this was our last discussion. Before we close our discussion, very important thing, I will just show you like how do we get the quantiles. Okay, and I will try my best to run the programming or RStudio with recording. Sometimes it's like quite complicated thing to do this. Studio. Okay, so I guess I'm hidden here. Just a second, I'm unable to see anything. Okay, now see. Don't bother about this programming part. I don't know why I'm not visible. Maybe some programming setting, but I'm here only. Okay. So only screen. Just a second, let me try to view this here itself. Let's see if it's possible. Yeah, it's working. So just a second, remind me later. I will do it. There is some transition issue. Okay, I will directly show you here itself. Okay, just see the screen, forget me. Okay, assume I'm not visible. Okay, now see here. So first step, so don't bother about the codes and everything. Okay, so in case you are not taking any programming classes, then it will be difficult for you. If you are taking programming classes, then we will cover this in programming classes. Okay, now just see here. So first part is, now we have to create a quantile-quantile plot. So first I will show you how the quantile plot will look for the normal data so that you can compare it with like the next non-normal QQ plot. Okay, so first of all, my task is to create QQ plot. So always specify it like that. And first we will start with, we need normal data. Okay, so first we need to generate normal data, and for generation we will use the rnorm function. So ndf, this is where I will store my data. Okay, and then rnorm, and in rnorm I need 1000 data points with mean is equal to 0. Focus on my words. Mean is equal to 0, standard deviation is equal to 1. Okay, now this is our data. Just to show you, ndf is our data. This is how your data looks like. See this. Okay, we can't understand anything from this, so we should plot histogram. And now see histogram. So histogram clearly tells us our data is normally distributed, or at least approximately normally distributed. To check it in the proper density distribution, okay, so we have habit of seeing density plot, right? So whenever we draw some density type plot, that bell curve or bell shaped curve, then that's a density plot. So let's see how it looks, how this our data, the randomly generated data, looks on the density plot. So we'll use ndf again, and let's plot the density or create the density from ndf. So we are using the ndf only. Okay, now we will plot our in.df. See here, not perfectly normally distributed, but still we can say this is normally distributed, right? So good enough. I would consider this as normally distributed. Now let's plot the QQ plot. So QQ norm is the function here, and we have to plot the, see this, your QQ plot. Okay, I will also add QQ line here, and let's set this line it, and set it 3. Okay, now let's see here, majority of these points are on this particular red line. Okay, and on the in the end there is some kind of deviation, but very less number of points are like this. Okay, so if this is the situation, we can still consider the data as normal. See, in real life, this particular scenario is never a problem, because we generally assume normal data. Even if there is some deviation, we go ahead with the normal data, assumption of the normal data, because if we don't assume normal data, then there is a deadlock situation, right? Then we have to work on sampling distribution. There is a lengthy process for it. So generally, if there is small deviation like this, we'll go ahead with the normal data assumption. But in the exam, if you see the points here in this range and points here in this range, but rest of the points are like this, then you have to assume that the empirical data, see here, this is sample quantile, means empirical data, and here you have theoretical quantiles, means your normal distribution quantiles, like this. Okay, that's why this is starting with 0, goes up to 3, minus 3, and like this. Okay, now let's see the actual data. Okay, instead of just a second, now we will compare this with actual / empirical data, and for this we'll need some data. Let me check the data set, some good data set. Here we can use, say, Johnson & Johnson, which provides quarterly earning, but this is time series data. Or we can also go with the plant growth. Okay, plant growth provides the cross-sectional data. Now let's see how the plant growth data looks. Plant growth, in this we have weight. Okay, so we have data here which is proper. We can work with this data. Okay, now let's start with again QQ norm and plant growth weight, and here you can see lot of deviation from normality. Now QQ line need plant same weight. and see here, this data is not normally distributed. Like enough information is available here. Okay, you can also check the Johnson and Johnson. Okay, now let's plot Johnson and Johnson. This is time series data, but let's do it. Okay, so why bother about the time series and all? We will just extract this particular part. Okay, so QQ norm, Johnson and Johnson, and see, not at all normally distributed data. This is apparent. Okay, so not at all normally distributed, because there is trend, there is seasonality, there is this data is time series data. That's why it is not showing you as a time series data. Okay, now this is about your normal distributions. Now we will compare this with our students tree distribution. So on the x-axis we will keep normal distribution, on y-axis we will get our empirical distribution, which is a students tree distribution, so that we can see clearly like what is a factorial problem here. So first we will start with generation of students tree data, and for the generation of students tree data we will store it in st.df. so just for like a reference, students data. Okay, so data generated from the students, and function which we are using here is the rt function. We have to select total number of observations we want 500 observations, and degrees of freedom, because students distribution is based on degrees of freedom. So here we will take degrees of freedom is equal to 30. And now let's plot QQ norm st.df, and here we have some deviation, but this particular deviation is not always visible. Okay, sometimes it's visible, sometimes it's not visible. It totally depends upon like your data. st.f, this is still looking like proper, but yeah, this is factorial. If I rerun this again, or just simply take 100, then this is like slightly away from normality, and we can see the curves here like this. Okay, so this is how you can check your normality. Even the students tree distribution, when you are taking, I'm taking 100 samples. Okay, if I take 20, then your graph won't look proper. Okay, like this. See, that's why I was taking 100. With 100 samples, automatically it will reach approximately to normality, right? So like this. So that's all about the QQ plot. Now I'll close this, save, display close on. Yeah. So that's all about our first chapter of market risk, and make sure you remember all the key points here. So key points is the game. Okay, nothing else is important in this chapter. If you remember key points, then this particular chapter is easy to go, not at all difficult. Fine. So that's all about the first chapter. Thank you for watching, and thank you for listening. See you in the next video. Bye bye, take care. If you have any queries, please ping me.